That's going. Thank you everyone for coming today to the GISS Lunch Seminar. I'm really happy today to have Kevin DallaSanta, who's an NPP fellow who's been working with me and some of the other people in the dynamics group, specifically looking at the high resolution version of Model E in the context of the Quasi-Biennial Oscillation and some other things about stratospheric variability. And so today, Kevin is going to give us a summary of some findings he has, looking at some of the CMEP6 runs that have been done. And before I pass it over to Kevin, I just wanted to remind people that, as usual, we'll be taking questions throughout the seminar. So if you do have a question, please just indicate in the chat that you have a question. You don't have to write it out, just indicate that you do. And then I'll unmute you. Everyone should be muted upon entry. That's the default. So if you have a question, just indicate in the chat. This is being recorded, so for people who can't attend, they can catch it later on the YouTube site. But aside from that, I'd like to welcome Kevin, and I'll pass it over to you.
Thanks. Thanks, and just stop me if there's a question that I missed. Since I don't have the chat window open.
Okay.
I just wanted to share, since nobody's coming to my apartment, I wanted to share how well my amaryllis is doing. I'm very proud. So it's been nice to have a little bit of color while locked down at home, working by myself these last few months. So as Clara said, she and I have been working on the Qbo in E2.2. It's work done with David, Larissa, Jeff, and Tihan, and having their contributions and insight has definitely been valuable, especially working from home over the course of the pandemic. So the Quasi-Biennial Oscillation may be familiar to many of us, but not everyone. So I'll start off by kind of introducing what that is. It's fairly straightforward. Then I want to talk about its period and amplitude and how those change with CO2 and in the future. And then I'll move sort of to more applications. So the Quasi-Biennial Oscillation has a signature on stratospheric composition on trace gases. It's affected by volcanic eruptions, as I'll show. And lastly, I'll talk about Qbo disruptions in the model and relate them to some of the real-world disruptions that we've seen. So the story of the Qbo is actually a very fascinating history. It's a lot of interesting details, but a good starting point is the 1883 eruption of Krakatoa in Indonesia. This was a large volcanic eruption that injected ash and aerosol into the lower tropical stratosphere, although people didn't know what the stratosphere was yet. And that ash and aerosol was visible as it traveled the globe 3 times at speed of about 30 meters per second. So the general idea was that you have easterlies in this part of the atmosphere. And there was very little evidence to contraindicate that until 1908. So from 1883 to 1908, a German group led by Beersen did a series of balloon measurements in tropical Africa. They took manned and unmanned balloon expeditions. The manned expeditions are rather dangerous because you have 2 people go up and take measurements until one person passed out, and then the other person would hopefully lower the balloon in time. So they did figure out that they could send unmanned balloons, which reached higher or less dangerous. And from those unmanned instruments over tropical Africa came a measurement of westerly winds in the lower stratosphere. So this finding was met with some skepticism, but Beersen was quite confident in the experimental design, and there was no total explanation until the 1950s, when the data coverage was sufficient from regular ballooned radiosonde campaigns to establish the full picture of what's going on. So tropical easterlies at one time, tropical westerlies at another time. And in the 1950s, it was discovered that this is part of a continuous global oscillation in the tropical lower stratosphere. So this is data from MERA-2. I simply plotted the zonal winds over the equator from 2000 to 2016. And what you can see are alternating bands of easterly and westerly winds, going from about 30 kilometers or even higher, 10 hectopascals, down to about 15 kilometers, 100 hectopascals. And the period of this oscillation is about 28 months. It's been observed to be very stable since the 1950s. So the blue and red alternations are quite regular until 2016, or 2015, 2016, when there was a disruption for the first time. So I'm not sure if my cursor comes through on here. Yeah, I think it does. So there's this, the red crosses over the blue right here. Something funky is going on with the blue. So that was the first observed disruption. And then in 2020, something funky is also going on. We don't have the clear easterly branch. The blue branch is somewhat pinched off by these westerlies again. So whether these changes, these disruptions are more likely in the future is unknown. And the changes to the QBO's amplitude and period are also a matter of ongoing research. So understanding these changes is important. The teleconnections that the QBO has for weather predictability, which actually changes based on the phase of the QBO. For stratospheric composition, which, as I'll show, is influenced by the QBO. And of course, at a modeling center, we would like to have a faithful atmosphere, capture the phenomena that are going on in the real world. So this is, again, the large-scale oscillation of the zonal winds in the tropical stratosphere. In the 60s and 70s, there was a lot of theoretical work to understand what was driving this oscillation. And the short story is that vertically propagating gravity waves turned out to be a crucial ingredient. So these are waves below the vertical resolution, generally. Planetary waves and tropical waves aren't sufficient, generally, by themselves. And we can achieve the gravity waves in a number of ways. First, we can use a high-resolution model. The question, of course, is how high is high resolution? A study in 2010 used 256 levels and had some sort of a QBO in their model. A more common solution is to add a fixed source of non-orographic gravity waves. So we take the troposphere, we send up gravity waves at a constant rate, and then tune those properties in order to get a realistic QBO in the tropical stratosphere. So this is the most commonly employed solution. It works for some purposes, but it has a disadvantage in that it's fixed. If the climate changes, do you keep the fixed source of gravity waves, or do you retune it? Do you make some assumptions about how it changes? It's not great if you want to look at climate change. And a better approach is to use an interactive source for gravity waves that does change in climate. So commonly, convection and shear are used as dominant gravity wave sources. This approach was pioneered by David's 1988 paper, which I believe is the first to do so. And the way that works is illustrated on the right. So the parameterization has 4 different gravity wave fade speeds. And I'll simplify the picture a little bit, just for the sake of demonstration. The x-axis is the QBO phase from 0 to 360 degrees. The y-axis is height, and the gray is the QBO background winds. So what happens is that a wave starts down in the troposphere with a given phase speed, moves up until it reaches the critical layer, which is equal to its phase velocity. So here the QBO speed is -10, and the -10 wave breaks at that vertical level. The -20 wave makes it up a little higher until reaching the -20 level, and similarly for +10 and +20. So there's some details, but basically it's sourced from convection. We can see what's going on. We can see how the waves break, and it's very interpretable in a physically meaningful sense. Now, until recently, relatively few CMIP class models even had a QBO. For CMIP 5, the few ones that did suggested a future decrease of amplitude. For CMIP 6, about half of the models have a QBO, and a multi-model comparison, separate but parallel to CMIP, was organized as the QBO initiative. So this is looking into what sort of intermodal consensus can we say about the QBO. GISS did not participate in the first phase of the initiative, but we were participating in the second phase. And those results seem to suggest an agreement regarding the future decrease of QBO amplitude, but not an agreement regarding the future period changes. And the disruptions, like the one I showed, very much remain an open question. Little to no work has been done from a modeling perspective. And comparing these models is complicated by the differences in the non-orographic gravity wave parameterizations. A majority of models, as I mentioned, used fixed. A handful of them use a convective gravity wave parameterization. One model obtains Qbo with the help of its cumulus scheme. I think that's a Japanese Mirok model. So I'm not familiar with the details, but it goes to show that there's very different physics going on behind each of these QBOs, which are then tuned to be realistic as possible. For Model E and E2.2 specifically, that tuning was evaluated in great detail in David's 2014 paper, looking at how choices in the parameterization and also tuning can impact properties of the QBO. And more recently, the pair of E2.2 papers that David and Clara led evaluate the QBO in E2.2. And our focus here is on past and future changes to the QBO, using as a starting point some steady state simulations. So we have a pre-industrial control, abruptly doubled CO2, and abruptly quadrupled CO2 in 4 different configurations. The first is a non-interactive configuration, NINT, so only CO2 and water vapor is changing between them. Second, we have a Linos configuration. This is a linearized ozone scheme using the box model calculations, not the most recent version that Tyler has been working on. Third, we have OMA, which of course is fully interactive chemistry. And finally, we have a fixed CO2 configuration. So this is the non-interactive configuration, but the SSTs are fixed to a pre-industrial climatology. So the steady state results are in minor revision at JGR, and we're working next to apply those mechanisms to the historical and the SSP runs. So I'll talk first about the Qbo period and its changes with CO2. So on the right, I have the 4 different configurations, and the pre-industrial in blue, doubled CO2 in green, and a quadrupled CO2 in orange. And you can see that the CO2 decreases for the NINT, Linos, and OMA configurations by about a similar proportion. But for the fixed SST configuration, the period change is severely inhibited. So clearly SSTs are crucial to achieving the magnitude of the period response. And they're crucial in their relation to convection, which I'll discuss shortly. This is already known from David's 2014 paper and a number of other studies. So there's relative decreases that are greater for the coupled ocean models than for the fixed SST models. You'll also notice that the pre-industrial control period is increased between non-interactive ozone and the 2 interactive ozone configurations. This is consistent with other results. The mechanism is understood. Now, in terms of our agreement between GISS and other Qbo initiative models, there's not a consensus about the future period changes. Some have period increase, some have period decrease, and some have the same period. And you might say, well, you told me that a majority of Qbo initiative models are using fixed gravity wave sources, so what happens if we throw those out? Well, there's still 4 models in the Qbo initiative that have convective gravity wave drag. 2 of them have a period decrease, like ours. 1 has no change, and 1 has a period increase. So there's not yet a consensus on the sign. Clearly, we want to dig into more detail as to how the period may be related to SSTs and to convection. So we do that with several different types of analysis, and basically what we find is underscoring is, the original link, that the period decrease is tied to changes in convection. In particular, an increase in convection sends up more gravity waves from the troposphere to the stratosphere. The wave breaking is in phase with the downward propagation of the QBO. So the QBO period decreases. One way to test that is by looking at the pattern of convective flux, which I've shown in this figure. So the top row is the climatology for each of the 4 configurations. You can see it's fairly similar. And the bottom row is the response to CO2. So we have a complex pattern that's nevertheless quite similar between the 3 coupled ocean configurations, just as the period changes are quite similar. Then for the fixed SST configuration, we have relatively little change to convection, just as we have relatively little change for the period. So this is consistent with the mechanism we've identified, and it suggests that models that have fixed gravity wave sources that do not have this kind of response are maybe missing a crucial pathway for the Qbo period changes. So that's +1 for GISS, which is great. However, there's also kind of a minus related to the climatology of convection. So we have, of course, a double ITCZ bias in the climatology, and how much impact that may have on the Qbo period and the Qbo changes is not clear, since the climatology clearly impacts the response of convection, and that response to convection impacts the period. So there's certainly more work to be done, especially comparing between other models. As another test of this hypothesis, we compare the Qbo period and convection in the historical and SSP runs. So on the left, I have the historical, on the right, the SSP runs. The first column is the Qbo period across the historical simulations, and then we have convection, convective and random flux on the right. There's 4 different configurations here, the 2 physics versions of E2.2 and the NINT, and OMA configurations. So what we see is there's little to no trend in the historical record, but there's a decreasing trend of the period in the SSPs, consistent with the increased CO2 results that we found for steady state. And it's also nice that we see a little bit of correlation in terms of the low frequency variability here. It's modest, but it goes to suggest that our mechanism is on the right track, despite all the other noise in the atmosphere. That's a brief primer on our Qbo period results, and I'll move next to Qbo amplitude, showing very similar figures. So again, with increased CO2, we have 4 configurations. The amplitude is decreasing for all of the coupled ocean configurations and for the fixed SST configuration. So clearly, what's going on for SSTs is not as crucial for amplitude. We're getting similar changes for the fixed SST configuration. Now, in terms of the pre-industrial control, the blue bars, you'll note that the amplitude increases from NINT to LINOS and OMA. So with interactive ozone, those ozone feedbacks enhance the Qbo amplitude. And this is well appreciated from previous studies, but we also note that the Qbo response, the amplitude change, is much shallower for OMA and LINOS as compared to the NINT configuration. So what's happening is that ozone feedbacks are modulating the amplitude response. They're acting like a shock absorber for the CO2 changes. They're muting that future change. So this is a novel result, and I'll explain shortly kind of how that works in a more specific way. The E2.2 amplitude, we link it to upwelling, so air moving up from the tropical troposphere up to the stratosphere. That speed is linked to Qbo amplitude, as other studies have discussed, and as I will show shortly in more detail. So to look at the amplitude response more closely, we first separate the easterly and westerly phases of the Qbo. So the easterly phases of the Qbo reach at almost 40 meters per second in the upper stratosphere, and then the amplitude of those easterlies decreases as we go down to the base of the Qbo. The westerlies reach about 20 meters per second, so there's an asymmetry between these, and the vertical structure is somewhat different. So you can imagine that the Qbo amplitude response is already a little bit more complicated than a simple scalar measure may suggest. So looking at how those change with CO2, we see that the easterly changes are peak at about 50 to 70 hectopascals, whereas the westerly changes decrease all the way towards the bottom of the Qbo region. So there's an asymmetry in the response, and the response is vertically dependent. To understand why that is, we look more closely at the upwelling changes. So here I have the ratio of the 4 times CO2 tropical upwelling divided by the pre-industrial control. And what we see is that for the coupled ocean configurations, there's an increase in lower stratospheric upwelling. And then that increase tails off in the middle stratosphere and upper stratosphere. So there's a couple of things to note. One is that this increase is in tropical upwelling is present for the 3 coupled ocean configurations, but not for the fixed SST configuration in all it. And similarly, we note that the westerly response is basically 0. Basically, the ratio is 1 for the fixed SST run in olive, whereas there's a clear decrease for the coupled ocean configurations. Now, in the middle stratosphere, we have an increase in upwelling for all 4 configurations, just as we have a decrease in the easterly amplitude for all 4 configurations throughout the stratosphere. So there seems to be an asymmetric link between the upwelling, vertical structure, and the impact on the westerly and easterly phases. You may also note that the black line here, the non-interactive configuration, there's a greater response in mid-stratospheric tropical upwelling as compared to the 2 coupled configurations in brown and interactive ozone configurations in brown and purple. We can understand that by looking more carefully at ozone feedbacks. So to get that tropical upwelling suppressed, to prevent that change from happening in CO2, what we see is that there's an increase in tropical stratospheric upwelling, moving ozone from the lower stratosphere up towards the middle and upper stratosphere. So ozone decreases below about 20 hectopascals, and it increases above about 20 hectopascals. That diabatic heating increases the stability of the atmosphere, so further vertical upwelling in the black line is suppressed here. And when that vertical upwelling is suppressed, we also get a change in the easterlies here. So this black line, this decrease that we find for the mid configuration, is inhibited, and we have relatively little change to Linos and Oma, the coupled ocean configurations. So on the previous slide, when I showed the bar graph, that amplitude modulation by ozone feedbacks is concentrated in a very specific part of the atmosphere. And in as much as this result holds for other models or for the real world, it's important to consider these contrasts and break them down in order to use observational data to understand how much the Qbo is actually going to change. So that's a complicated but a dynamically consistent explanation of what's going on with Qbo amplitude. And we can once again test the hypothesis by looking at the historical and SSP configurations. So on the left, historical, on the right, SSP, and then I have Qbo amplitude and tropical upwelling, 70 hectopascals on the right. What we see is a recent decrease, if anything, of Qbo amplitude, and then for SSPs, that decrease seems to become strengthened. Qbo amplitude continues to decay in time. And we have associated changes with tropical upwelling, although as I showed in the previous slide, relating those changes is complex and sensitive to the vertical level. So that's the gist of our period and amplitude results, and I'll next move to a few applications. Oh, before doing that, I also wanted to talk, as the slides remind me, about the Qbo amplitude in the model and our desire to improve the vertical structure. So I have here plotted the total acceleration composited across 360-degree phase for Merit 2, ERA interim, and NIT, the E2.2 coupled ocean configuration. So the reanalyses are in decent agreement. The Qbo extends down to 60 or 70 hectopascals, whereas for E2.2, there's almost nothing going on below 30 hectopascals for these contour levels. So what that means is that the Qbo is too weak in the model as compared to these reanalyses. And it's not something we can simply fix by tuning, as David's 2014 paper looks into. This constant, the convective efficiency factor, SCVMU, if you use the model, helps with the Qbo period very closely, but has less impact on the vertical structure of amplitude. So it's not something we can simply tune to get the right vertical structure. We can, however, break this momentum budget into its component terms. So we have transform convection on the second column. We have the resolved waves on the third column. And then we have parameterized waves in the fourth column. And the key result here is that the westerly forcing in reanalyses that I've highlighted in the red box is too weak in the model as compared to the reanalyses. And that's related in particular to Kelvin wave forcing, which supplies westerly momentum. And we're interested in what kinds of ways we can enhance this momentum. So that may be by increasing the vertical resolution, perhaps using that result in order to further parameterize the Kelvin forcing. We've also thought about adding a stochastic component to the gravity waves so that we could deposit some of the momentum where we're hoping to get it. But there's no guarantees as to what will happen because there's a strong compensation between the resolved and the unresolved waves. As we can see from the bold colors down here and the comparatively light colors up here, which when you add them up, give similar magnitude of colors in the total change. So I'll move now to a few applications. First, looking at the Qbo impact on stratospheric composition. The Qbo has a clear signature in trace gases and age of air, as I've shown on the right. First, we have Linus ozone and Omo ozone, the time average, and the Qbo. Here I've just shown the pre-industrial oscillation. And overall, there's great agreement between Linus and OMA, especially considering Linus was derived from the simpler box model calculations. Suggests that those are sufficient in order to capture the first order changes that are going on. We have methane, and the changes to these tracers are consistent with changes to vertical advection. So there's no crazy photochemistry that happens as soon as we hit 4 times CO2, or 2 times CO2 for that matter. One interesting result is related to water vapor. So you note that the time mean water vapor has relatively little vertical gradient. It's fairly uniform throughout the tropical stratosphere. And the tropical stratospheric water vapor is dominated by the so-called tropical tape recorder. And in a 2002 paper, Marv Geller, Tihan, and colleagues observed that the tropical tape recorder was modulated by the QBO, that you could detect QBO signal between phases in the water vapor, but they speculated that ENSO variability of the tropical tape recorder might swamp out the QBO response in the long term. So if you average over a long enough time interval, you'll see, they speculated, you will see relatively little impact of the QBO and water vapor. And indeed, that's what we find. So I've highlighted in the box that we had used a nonlinear color bar. These changes in the mid-stratosphere are much weaker than the changes at the bottom. Water vapor clearly behaves differently than the other composition QBOs. So this is a small but a nice result confirming the 19-year-old conjecture. Unfortunately, not one of the Millennium Prize conjectures, but we will take what you can get. So number 4, another application is looking at the effect of volcanoes on the QBO. So as you probably know, volcanic eruptions are able to heat the lower stratosphere. On the top row here, I have temperature anomalies for 2 different models. These are 2 members of the same ensemble. And after Krakatoa in 1883, we have heating of the lower stratosphere that I've highlighted in the red box. Now, heating is associated with the anomalous westerlies. And this model on the left, the westerly phase of the QBO was just about to end. But after 1883, it's prolonged so that that phase lasts a little bit longer than it would have otherwise. In contrast, if we had easterlies coming down, like this member, they're truncated early. That branch kind of rushes to finish up because we have this big influx of westerly momentum in the lower stratosphere. So the QBO is either kept in a westerly phase down here or nudged toward that westerly phase more prematurely than otherwise. We can quantify that by looking at the starting phase, whether it started at a westerly or easterly phase for all these different ensemble members. And what we see is that compared to the average on the solid lines, the ones that started on the westerlies have relatively little phase change in the year following the eruption, just like this one here. And as we start in an easterly phase, these ones up here move very quickly, like the member on the right. And then we can draw that trend line back down again towards a westerly phase. We can also check this hypothesis for Pinatubo. So Pinatubo was a weaker eruption, but we still see this sort of triangular shape to the response, where the starting phase makes a big difference in how fast the QBO moves afterwards. You'll notice that Merit 2 does sort of lie along this trend line. It would be great if Merit 2 was up here or down here, but I guess with observations, we have to take what we can get. So there does seem to be a clear story about the QBO period. The story about the QBO amplitude it's not as clear. It's very noisy and doesn't have as simple of an interpretation.
Hi, Kevin.
Yeah,
I have a question on this. So before with the abrupt CO2 runs that you did, there was a clear modulation of the CO2 amplitude response in the OMA integrations, wherein you have interactive composition. Do you see that interactive composition also modulates this kind of relationship in terms of the QBO phase change dependence on its initial starting phase? Is there anything that you're seeing that OMA is that these feedbacks that you would be getting in OMA are somehow modulating that?
That's a good question, and I think a short answer would be it's hard to say to make that statement just statistical significance. So, for example, we have the blue members, which are non-interactive of the altered physics configuration. And then we have the green members here of OMA. There's, I think, 4 of the green ones and 5 of the blue ones. So do we say that there's a statistically significant difference between this group up here and this group down there? Is it the difference in interactive chemistry is causing the difference between these blue ones and these green ones? Or is that merely like a statistical noise that that the trend line does come up here? The trend line is spiking up here and coming down. I'm not sure how to rule that out statistically, but there could be a dynamical explanation. So that's a good point that we can look into.
Yeah, that'll be nice to look at. We should actually look at the ozone response too there. I think that Allegra has some kind of related questions. Allegra, instead of reading these, would you like to just maybe ask them? Let me just, oh, there you are. Okay, you're unmuted. Yep.
Sure. Krakatoa really wasn't that much bigger than Pinatubo. I mean, it was probably pretty similar in size. I would guess that the biggest difference is like what's going on in your background climate. Like Pinatubo's got the CFCs. Mm-hmm. And also you have maybe different solar forcing. So both which would project onto what your ozone was like relatively at Krakatoa versus Pinatubo. So what is that not a more plausible? I don't understand what you say it was bigger.
Yeah,
like did you just suppose it to be bigger?
Yeah, offhand I would assume the solar cycle could play a difference. I should check what phase Krakatoa and Pinatubo are. In terms of the CFCs, I guess that again brings up the contrast between the NINT and the OMA configuration. So the CFCs shouldn't make a difference between Pinatubo and Krakatoa.
No, that they wouldn't make the CFCs themselves.
In terms of the described ozone, yeah, that's true. That's a good point. So, yeah, that's something we should look into. Thank you.
Thanks.
Great. Okay. Well, if there's some further questions, please interrupt or send me an email. I'm happy to share some more results or share these figures. So we'll talk in the next and last section about Qbo disruptions. As I mentioned in 2015, 2016, there was the first observation of a disruption. It was kind of a surprise because the Qbo had been so stable up to that point. So it kind of created it raised a series of questions for the modeling community. How do our models simulate disruptions, and how can we relate those results with all the problems of a modeled Qbo to the real world? So there's been little to no work looking at disruptions of the Qbo from a modeling perspective, and that's something that we're hoping to make a substantial contribution to. So what we do is we've developed a novel metric to measure these disruptions over a long integration. And the basic idea here is that a value of 1 means that the Qbo is disrupted, and as we move towards 0, the Qbo becomes more disrupted, becomes more chaotic, and then it may recover and go back to 1 with a stable Qbo. So this is just merely one example from one integration. Happens to be after Krakatoa with the anomalous westerly forcing. So the Qbo was fine and dandy until about the eruption time. Then it decayed. We had nearly continuous westerlies throughout the tropical stratosphere. And then the normal behavior of the Qbo reemerged, the associated dynamics taking place. So let's take this metric, which measures from 0 to 1, and apply that to one ensemble, just as an example. So these are the standard physics NINT members with steady state CO2, so pre-industrial, 2 times and 4 times. What we see is that the disruptions are relatively infrequent for this ensemble. There's a couple for pre-industrial, a couple for 4 times that are fairly severe, and then maybe some minor disruptions, more moderate ones, but none of them last more than, they last on the order of months, not on the order of years or decades. They appear, the Qbo is able to reemerge and reestablish itself. So this is one ensemble, and now I'll show all the ensembles we had in a big plot. So on the left are the historical runs, and on the right are the steady state CO2 runs. And there are several contrasts that become apparent just by comparing different parts of these panels. So first is a contrast between altered physics and standard physics. So it seems that standard physics has more disruptions as compared to the altered physics configuration. Oops. Here. Okay. So altered physics to standard physics, and then here's the corresponding pair for OMA and historical. And then we have the NINT steady state CO2 simulations. Again, if anything, there's more disruptions in standard physics. There's also apparently a contrast between the historical runs and the CO2. So that's this pair here, this pair here, and this pair here. It seems that the steady state simulations have relatively fewer disruptions as compared to the historical runs, suggesting that the extra sort of year-to-year variability is a problem for the Qbo stability. You also see a contrast between NINT and OMA. So that's this ensemble versus the third row here, and then this one versus this one. And then the steady state runs, we have this one versus this one. And each of those, OMA seems to have a positive effect for Qbo stability, that the chemistry feedbacks, if anything, are enhancing the stability of the Qbo. So we'll talk more about that in just a second. But I want to note that the disruptions are loosely fall into certain patterns. So the one I showed was just one case study. We can apply that same analysis to all of these spiky disruptions coming down. And what we see is that they're fairly heterogeneous, but loosely speaking, they seem to take different patterns. It's not as simple as saying type 1, type 2, type 3, but some patterns emerge, maybe family 1, family 2, family 3, enough for us to identify the dynamical mechanisms Some of them are caused by anomalous EP flux. Some of them have anomalously strong vertical advection. So that's something we hope to make progress and understand. In terms of what sets the disruption frequency, we've looked into a bunch of different possibilities. An initially appealing one is ENSO variability. So as I mentioned, we might think, oh, well, the historical runs have more variability at the lower boundary. We've already tied convection very closely to the QBO. So maybe there's some sort of correlation between variability of tropical SSTs and the percentage of months that are disrupted in the QBO. So when we, this was a good lesson for me, I guess, as a scientist, because when I looked at these first integrations, I say, well, that's great. There's our mechanism. But when we add the steady state CO2 simulations, that linear relationship is much more tepid. These steady state CO2 simulations with coupled ocean have high NINO 3.4 variability, but they have relatively little disruptions. So this is still possibly related, but not a clear predictor for how often these disruptions occur. Another hypothesis is that the semi-annual oscillation is important. So the idea here is that a stronger SAO, which spawns the QBO branches, if those SAO anomalies are stronger, then the start of the QBO will be more robust, have more momentum to defend against other incursions of momentum from anomalous EP flux, vertical advection, etc. So here again, there seems to be a nice sort of linear relationship between them, but again, correlation does not necessarily give us causation. So we want to parse this from a dynamical test. One of the immediate questions which we've identified is that the pre-industrial simulations here have much higher SAO amplitude compared to their historical counterparts. So this is a little bit surprising, and we're looking into how ozone or other factors may be related to that contrast. So I think in pretty good time, I'm just wrapping up with some conclusions. E2.2, as we've seen, has a decrease in Qbo period and amplitude when we increase the CO2 or run some more specific SSP scenario. The interactive ozone is a particular contribution of our study. It seems to matter for getting the amplitude trends right, and Linos seems to suffice. So we may not need to run a fully interactive scheme. Merely a linearized one might do a good enough job. If anything, other non-interactive models may be overestimating the amplitude response, assuming that this sort of ozone feedback on amplitude behaves similarly. And we hope that looking at the contrast between westerlies and easterlies can provide insight into those differences. Future changes to the QBO, especially the Qubio disruptions, can be sensitive to model biases, such as basic state, convection, upwelling, and chemistry. And the point here is that certain changes may be more sensitive to certain parts of the model. So if upwelling doesn't seem to matter so much for the QBO period, then we don't need to worry as much about the differences between models. And hopefully we've made progress in understanding which aspects are more robust related to which mechanisms. So in terms of the ongoing and planned work, we'd like to improve the model's vertical structure in order to get the QBO propagating lower, more similar to reanalysis. We're analyzing the disruptions in terms of what sets the frequency, how they work in SSPs is ongoing work. We also plan to participate in round 2 of the Qbo initiative, which has some experiments looking at the role of sea surface temperatures. As I mentioned, the CO2 results are in minor revision, and the historical SSP results are in preparation. So thank you very much, and I'm happy to take questions.
Great. Thank you, Kevin, for that review. So at this point, okay, I see that David has a question that you put in the chat. David, do you want to ask the group? Yeah.
Yeah. Thanks, Kevin. That was a wonderful, clear talk. I guess the comment well, there's one comment and one question. So I think we know that the comparison you showed between observations and the model, I think it was at the end of your section 2,
Okay.
showing the weakness below 30 hectopascals.
Yeah, do you want me to flip to that, or do you want to use this figure?
Yeah, thank you.
Flip to the other one?
Yeah, please. Yeah.
Okay. That's this one, correct?
Well, so when you actually showed the comparison with observation, yeah, there we go. Yeah. So I think we know that if you use the OMA configuration as opposed to NINT, the model does have more a greater Qbo amplitude in the lower stratosphere.
Yes.
And I wonder in what that shows up under, if in fact that is the case. Would it be the transformed advection that's extending further down? Would it be the resolved EP flux divergence? Because it's involved with the movement of ozone from the troposphere into the lower stratosphere. I just wonder exactly where that would show up. I don't know if you have looked at that.
Yeah, I plotted EO7, but I haven't taken the difference. So that would be repeating this third row for the OMA configuration, just like we did for the CO2 results, and then taking the difference of those two to see, as you said, where that changes. So definitely, I can follow up with you on that.
Yeah, and the other question I have relates to this idea that with interactive gravity wave forcing, models are getting different results in terms of what actually happens to the period. One thing that's known is that models are all over the place in terms of what their future changes in SSTs are in the tropics. And that is related to people believe, to the different cloud cover schemes that the models are utilizing. I wonder, have you seen whether there are, so for example, let's say the Eastern Tropical Pacific in one model really warms up in 2 or 4 times CO2. And in another model, that region doesn't warm up, but maybe the Indian Ocean warms up. Do you think any of those regional heterogeneous variations in tropical SST response could be influencing this question about the period?
That's definitely a possibility. I think of the QBOI papers that have been released so far, Laura Holt's 2020 paper may be the most applicable. So that was, I don't remember if we'd sent that around. That was the one looking at tropical waves in the model. And I don't remember that there was a breakthrough explanation in terms of SSTs, but it may be that phase 2 of the QBO initiative will provide more insight into that, since there's specific ENSO perturbations that are prescribed. But that's perhaps something we can make a contribution if we are able to obtain the other QBOI data.
Yeah, and then the other thing that sort of obviously comes to mind is models have different degrees of penetrative convection schemes. So one might imagine that too would have some impact.
Definitely, yeah. It can be a bit of an apples and oranges comparison. At least a Granny Smith apples versus Fuji apples versus
Red Delicious.
Red Delicious. No Red Delicious. Worst name ever.
Thank you.
Great, thanks. Well, so just on that last point, I do think it'll be interesting, even not appealing to the QBOI models, but to look more in-house, Kevin. At some point when the E3 results come out, we do know that E3 does have QBO too. I think it'll be interesting, given the differences in convection in that model, to see too if the period decreases that you see in E2.2 are also exhibited in that version of the model.
And the differences that numerics have on tropical waves.
Yeah. So I think David's points there are really good, and we can then kind of think about, and I think Anne is making a comment and across our ensemble. Yeah, definitely. So
if anybody has any other runs they would like me to look specifically at, please do let me know.
So I also had just one other question, which was in relation to kind of evaluating the QBO. So traditionally we tend to think about, we assess the QBO in terms of these kind of very long down the chain metrics, like is the period right, is the amplitude right, owing to our inability to actually observationally constrain the forcing, right, from the momentum fluxes themselves. But I do think that more recently, we have been getting a better kind of satellite-based estimates of the full PDF, the full distribution of the momentum fluxes, which in some sense is a comment in terms of the model's ability to represent the intermittency of those fluxes. And you had made a comment earlier about, wanting to explore how that might be impacted by things like a stochastic parameterization, even though, it should be mentioned that in the parameterization that David developed, there is an intermittency owing to just having convection and all these other contributions. But I guess my question is, have you done an actual evaluation of the PDF of the momentum fluxes? And if not, I think that would be really, really nice, and it would go towards more of this kind of higher order evaluation of the model, besides just looking right at the Qbo period and amplitude.
Mm-hmm. Certainly, that's something that could be done in terms of a tropical average or in terms of a grid point by grid point basis, because the double ITCZ may play a factor in that.
Yeah.
Great.
Great. So does anyone have any questions? Thanks a lot for the ones so far.
It was a really nice talk. Thank you, Kevin. I especially appreciated the little historical perspective at the beginning. It's really nice.
If you're, there's a book by Levitsky and von Loon on kind of the history of the stratosphere, and I find it very fascinating how they figured all these things out.
Thanks, Allegra. Great. So with that, still have a bit, like 5 minutes, but I guess I'll close this. I want to thank you, Kevin, again for a really nice talk. And thanks everyone for attending. And so like I said, this was recorded and will be posted probably within a week or so. And I invite you, along with Kevin, to email any questions you have about this and or related to E2.2 and some of the development and things that we've been looking at. So thanks a lot, everyone, for attending. And I just wanted to quickly advertise the next seminar we're going to have is on February 10th. The speaker is going to be Daniela de Mason. She's a professor at ETH Zurich, and she's going to be presenting a nice review of a lot of work that she's been doing looking at the role of the stratosphere in modulating tropical to high latitude teleconnections, specifically in the context of sub-seasonal prediction timescales. So she's a very nice, clear speaker. So I look forward to that. And I'll be sending a reminder announcement about that. So thanks a lot, everyone.
Thank you, Clara.
Thanks a lot, David.